Okay, so this next definition tells us how to find when a limit, when a sequence converges, and we would do this by evaluating a limit. We would take a limit of the sequence, of the general term for that sequence, as n goes to infinity, which is really saying, in a sort of informal sense, if we were to look very, very, very far down the list, what would the number be? This is another way of saying, what's the eventuality? To what this list of numbers, do they approach a specific number? Now, this list of numbers, it's infinitely long, so it never terminates. But this notation, this notion, the limit as we look further and further down the list, that tells us, that will allow us to determine whether or not this sequence converges if we have a formula for it. We might not have a formula for it, and then there's a little bit more work that needs to be done, but essentially we will take a limit. So if we go back up to the previous example, we can see that a sub n is 1 over n. And the limit, as n goes to infinity of a sub n, is just the limit of 1 over n, which is 0. And that is the value to which the sequence converges. Now b sub n, on the other hand, that's just equal to n. So if we take the limit as n goes to infinity of n, we just get infinity, which means we have divergence. So we get the same result as what we got in example 2. Okay? So here, this theorem just relates the limit of a continuous function and the limit of a discrete function. So remember that we can think of a sequence as a discrete function. In other words, a function of a discrete variable versus a function of a continuous variable x. So a continuous variable x means it can take on any value it wants to within its domain. Where a discrete function, its domain might be all numbers greater than or equal to 0, but only the whole numbers. In which case it's discrete because it can't take on any value, but only these specific discrete steps. So if you have a function such as, let's take a look at what we had in example 2, we had the sequence a sub n defined to be 1 over n. So although this is a discrete function, and if I were to graphing it, I would just get these dots. Whereas if I were to graph its continuous analog, let's say f of x equals 1 over x, then I would actually connect the dots. So these dots are really the result of evaluating at different x values, or excuse me, at the whole number values of the discrete variable. But the important thing here is, as long as your discrete function and your continuous function agree at the whole numbers, then the limit of one is the same as the limit of the other. They agree with one another. So let's take a look at examples 3 and 4. So example 3, determine the limit of the following sequence. So in other words, this is, i.e., the same thing as, does the sequence converge? The way you check whether a sequence converges or diverges is you take a limit and see what that limit is. Does the limit exist or does it not exist? So in this case, if we take a limit of the sequence term, we'll get that this is equal to 1 using the method of dominating terms. We've got the dominating term in the top is n squared, in the bottom also n squared, so the ratio of the coefficients is 1 over 1, which is 1. So that's the limit of the sequence. We would say that the sequence of a sub n converges to the number 1. That's another way of saying it. Example 4, L'Hopital's rule. Determine if the following sequence converges. So an interesting thing, and this is why we mentioned this theorem 1, the importance of a sequence that is defined by a function, is if you consider this function, it's a discrete function. So it doesn't actually have a derivative, at least not in the sense of how you learned of what you learned a derivative to be in Calc 1. There is a rate of change associated with it. There is a sort of a discrete version of the derivative. But for L'Hopital's rule, we need the regular continuous notion of a derivative. And since this is a continuous function, since this is a discrete function, it's not continuous. And even continuous functions don't always have derivatives. But a discontinuous function most certainly does not have a derivative. So it might seem like a little bit of a technicality or a little bit of just extra work, but really, if we're going to use L'Hopital's rule, we're going to want to make sure that we first... So I'm going to just mention here underneath, I'm going to say that this is discrete. A discrete function doesn't have a derivative, at least not in the traditional sense. So that's the first issue. A discrete function doesn't have a derivative, so how can we use L'Hopital's rule? So what we do is we will pass to its continuous analog. So this would be, let's say a function, we'll define it to be f. So this would be f of x equals x plus natural log of x over x squared. So if we try taking the limit of this now, as x goes to infinity, we'll of course get something like the indeterminate form infinity over infinity. So to combat this, we can use L'Hopital's rule, which this function now has a derivative, at least where that derivative does exist. So using L'Hopital's rule, we would have 1 plus 1 over x over 2x and now if I split this up by dividing each term in the numerator by the denominator, we should have the expression 1 over 2x plus 1 over 2x squared. So in this case, we get 0. So that checks out.